We have been discussing the electronic Schrödinger equation for an atom or a molecule. So the problem the Hamiltonian is kinetic plus potential energy, and the potential energy is Coulomb energy. And we have discussed how to write down explicitly the Coulomb interaction among the electrons and the nuclei. Now, the kinetic energy. We start with a single electron moving in 3 dimensions. And the expression for the kinetic energy of a single electron is square of linear momentum operator divided by 2 times mass of electron. Now, we first start with writing the expression in SI units and then convert the units from SI into atomic units. So this is explicitly now, let us use the following notation. X bar, Y bar, and Z bar be Cartesian coordinates with length unit. In other words, in SI it is meters. And define dimensionless variables by setting x bar equals x times Bohr radius. Similarly, y bar is y times Bohr radius, and z bar is z times Bohr radius. We are going to take the unit for length as the Bohr radius. That's why we are doing this. Now, this expression for example, px square over 2 times mass of electron is minus, now the explicit definition of px square is minus h bar square times the second derivative with respect to x bar. And we have also this 2 times mass of electron. Now, using this definition for x bar, we can write this expression as minus h bar squared divided by 2 times mass of electron times A0 square times the second derivative with respect to x. Please note that even though kinetic energy, this is an operator, but nevertheless it has a unit. It's kinetic energy. Therefore, it has energy unit. In this expression, which is in SI units, the unit for energy is joule. So this expression has the net unit is joule. In fact, the quantity is h bar squared divided by mass of electron times A0 square. Numerical value of this expression is the same as this is Hartree. Remember, previously we had written it as E squared divided by 4 pi permittivity constant times A0. These two expressions have energy unit, joule, in SI units, and numerical values are exactly the same. You see, the constants here are different from the constants here, but when you do the calculation, you will see that this expression is the same as that one, which means that this we can write minus 1/2 times second derivative, and the unit is Hartree. We want to express the kinetic energy operator also in Hartree units because our potential energy is expressed in Hartree units. Kinetic energy must also be expressed in Hartree units, and that's how it is done. So this transformation into dimensionless units for x is also done for this term and for that term. The final result for the kinetic energy for a single electron is minus 1/2 del square. This is the Laplacian operator. It is sum of second derivatives this is in Hartree unit. All right. When we have more than one electron, and in atoms and molecules we have many electrons, the total kinetic energy operator is simply a sum of contributions from each electron. sum of kinetic energy contributions from each electron. We label the electrons, of course, by the integers 1, 2, 3, up to n. So explicitly, this is simply minus 1 over 2 times del J square. And we simply add up from J equals 1 up to n. So, you see, writing the total kinetic energy for n electrons is simple. It's simply additive. And the total Hamiltonian is that expression for kinetic energy plus the potential Coulomb energy for the potential energy. Let's have an explicit example. Lithium is an atom. The atomic number is 3. And this is neutral lithium atom. Therefore, it contains how many electrons? 3 electrons. So n is 3. Potential energy in Hartree units is electron-nucleus interaction plus electron-electron repulsions. Electron-nucleus interactions is minus 1 times 3 divided by R1 minus 1 times 3 divided by R2 minus 1 times 3 divided by R3. R1, R2, and R3 are the distances of the electrons to the nucleus. This is our notation. This part is electron nucleus interactions, or we may simply say attractions, electron-nucleus attractions, because electrons have negative charge and the the nucleus has positive charge. So these are attractive, as indicated by the minus signs here. We have also electron-electron repulsions. How many electron pairs do we have? Pair 1, 2, pair 1, 3, and pair 2, 3. The total expression is 1 over R12 plus 1 over R13 plus 1 over R23. This part is contribution from the electron-electron repulsions. All of these are in Hartree units. As you should remember, R12 means the distance between electron 1 and electron 2. Similarly, R13 and R14. The kinetic energy expression is simply minus 1/2. This is the contribution from the first electron. I'm just applying this expression. Minus 1/2 all right. So this is the explicit form for the kinetic energy part. and this is the explicit form for the potential energy part. The total Hamiltonian is this expression plus that one. In other words, H is T is this expression, V is this expression here. Let's have one more example, this time for a molecule. Take hydrogen molecule. And the question is the electronic Hamiltonian. Now hydrogen molecule has two nuclei. Let us label the nuclei with A and B. These have +1 charge, both of them. And there are how many electrons in neutral H2 molecule? There are just 2 electrons. So electron 1, electron 2. All right. Let us call the distance between the nuclei the symbol capital R. When we have just 2 nuclei in the molecule, it is not necessary to use AB symbols because we have just one distance, only one internuclear distance. A single symbol is enough for it. So here, Hamiltonian is kinetic plus potential energy. Let us write kinetic energy. First, we have just 2 electrons, minus 1/2 This is the total kinetic energy of the electrons, explicitly. All right? What about potential energy? Potential energy is electron-nucleus interactions plus electron-electron repulsions plus nucleus-nucleus interactions. This is repulsion. This is also repulsion. This is attraction here. You see, this term is the only difference from an atom, in a way. So, what is electron-nucleus attractions? Attraction of the first electron to nucleus A, minus 1 times 1 divided by R1A. Now this is distance. R1A means distance between electron 1 and nucleus A. Then attraction of the same electron to nucleus B. This is R1B. We are finished with the attraction of the first electron to both nuclei. Now we continue with the second electron. It is here. It is minus 1 over R 2A. 2A is this distance. Minus 1 over R 2B. Attraction of the second electron to nucleus B. That distance, R2B. This is the complete expression for electron-nucleus attractions. Electron-electron repulsions. How many pairs of electrons do we have here? We have just 2 electrons, so how many pairs? Pair means what? 2. only one pair. So the electron-electron repulsion is just 1 over R12. Minus 1 times minus 1 divided by the distance between the two electrons, which is called R12. What about nucleus-nucleus repulsion? We have just two nuclei here, which means just one pair of nuclei, each with charge +1, +1 times +1, which makes 1, divided by distance between the two nuclei. Which symbol did we use to denote this distance between A and B? Capital R. Okay, so here, electron-nucleus repulsion there, electron-nucleus attraction, sorry, electron-electron repulsion, this expression for this one, and nucleus-nucleus repulsion for that one. So that gives us the complete potential energy function explicitly. Kinetic energy is this term for the electrons, and the Hamiltonian is, you just substitute these expressions to kinetic energy and potential energy there. That makes the complete Hamiltonian explicit. And then you write down the Schrödinger equation explicitly and try to solve it. Fine. So I hope everybody can write down explicit expression for the total Hamiltonian, electronic Hamiltonian of any atom or molecule. Now we turn into solving the Schrödinger equation. And of course, we are going to start with the simplest possible case, and it is the atom with a single electron, which is the hydrogen atom. Neutral hydrogen atom. Hydrogen atom has a single electron, and it has a nucleus, which is a single proton with +1 charge. And the electron is moving around this proton. The Hamiltonian, kinetic plus potential energy. Kinetic energy is simply for when we have just a single electron, of course, we are not using subscript 1, 2, 3 because we have just one electron. This is the kinetic energy part, and the potential energy part is there is only electron-nucleus attraction, and we have just one electron. So it is not necessary to write 1A here, because we have just one electron and one nucleus. This R is the distance between the this is R, distance of the electron to the nucleus. The Schrödinger equation is now the electron has 3 variables because it's moving in 3 dimensions. In solving this problem, we need to decide on which type of variables we should use because we have more than one possibility. We may use Cartesian type variables, isn't it? Then we would write x, y, z. In that case, r has to be calculated from x, y, z. How? R square is equal to, if x value, y value, z value is given to you, can you calculate the distance, r? R square is x square plus y square plus z square. So if you think about this expression in terms of Cartesian type variables, this r is a short symbol for square root of x square plus y square plus z square. All right? On the other hand, we can also use, for example, polar type variables. Again, three variables, r, theta, and phi. When we use r, theta, and phi, r is one of the independent variables. In that case, this r is directly one of the variables. Okay? But then, the kinetic energy expression must be converted from Cartesian type into these variables. It turns out that using the second type, the polar type, spherical polar type variables, makes the solution of this problem easier. And I will show you how it is. First, Laplacian operator. In Cartesian type variables, this is simply sum of second derivatives with respect to each variable. Using the relation between r, theta, phi and x, y, z, this expression can be converted into r, theta, and phi. I'm not going to give you the details, but the net final expression is don't write this. I just want to show some important points in the expression. This expression for Laplacian in spherical polar variables is a more complicated expression than the expression in Cartesian type variables. Why? Because in Cartesian type variables, x, y, z, this is just second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. That expression is simpler than this expression. However, what you see here, this part is related to square of angular momentum. You see, this inside the parentheses, the only variables are theta and phi. Just two variables, and these are angle variables. This is in, if we take our definition for L square in SI units, this is L squared divided by minus h bar squared. This expression is dimensionless, no unit. When you use SI units for the angular momentum operator. So that the Laplacian operator takes the following form: an R-dependent part and the Hamiltonian is this expression minus 1 over r. Kinetic energy, and this is the potential energy minus 1 over r that you see here. We see that from the structure of this expression, it's sum of 3 terms here, but this term contains only r variable. This term contains also only r variable, and this term in the upper part, L square, as you see, contains the angle variables theta and phi. So now if we ask, does L square commute with this Hamiltonian? What do you say? Now remember our basic rule. Whenever you have 2 operators, one is A, the other is B, and they contain different types of variables, do they commute or not? Different independent variables, they always commute. So that simple rule is used here to answer this question. There are several terms here. So if L square commutes with each one of the terms separately, then it will commute with all of it. So start. L square, does it commute with this term? Second derivative with respect to r square. This contains only r variable. You have to remember which variables are contained in the angular momentum, theta and phi, different independent variables. Therefore, L square commutes with this term. It also commutes with this term. All right? Now we come to here, or this one. Again, it commutes, different types of variables. Finally, it also commutes with this term because it contains r square. L square, of course, commutes with r square because different types of variables. And it also commutes with itself. Any operator always commutes with itself. As a result, what do we conclude? Sorry, in this expression, this is first we have a minus 1 over 2 times this. And also this makes it plus 1 over 2 L square. Okay, So our final conclusion is that L square commutes with the Hamiltonian. Therefore, this is the Schrödinger equation, which will give us the energies and also the state functions of the electron. Whenever two operators commute, what do we conclude? Those two operators have simultaneous eigenfunctions. Here, one of the operators is L square, the other is H. We are trying to solve the eigenfunctions of H, Schrödinger equation. Now, this fact that L square commutes with H tells us that the psi's here must also be eigenfunctions of L square. But do we know the eigenfunctions for L square? Yes, we do. We have studied eigenfunctions of L square in the discussion of rotation of a molecule around its center of mass. Here we are talking about a different quantity. It is the motion of the electron moving around the nucleus. However, the mathematical problem is the same. Eigenfunctions of L square are spherical harmonics. These are known. These are standard functions. So, this psi must contain a spherical harmonic as part of it. It must have the form a factor which contains only the R variable multiplied with a spherical harmonic function. Because L square, remember L square L times L plus 1. Here there is also H bar square, but when we divide with this H bar square, we may write it directly in this form, L times L plus 1 in dimensionless form. Unit of angular momentum is H bar. Therefore, square of angular momentum will have H bar square as the unit. If you want to write it in SI units, then you will include the unit. For angular momentum, it is H bar. The square of angular momentum is square of H bar. So here, L is 0, 1, 2, and so on. So this expression is used in the Schrödinger equation with this Hamiltonian. This is known This is the unknown function. This expression is substituted to Schrödinger equation, and then simplification is done. Then one obtains another equation for R. Finally, the equation for R is minus 1/2 This is the equation for the R, capital R factor here. Now, you don't bother about the terms in it, but just think in your mind how, whether or not there is simplification. The original equation contains how many variables? Independent variables, 3 independent variables. So this is original equation is a partial differential equation in how many? 3 variables. All right? Noting that the L square commutes with H, and because eigenfunctions of L square are already known, this problem is converted into this problem for R. And here in this problem, how many independent variables do you see? Our variables are R, theta, phi. How many of these variables do you see in this expression? Only one of them. Which one? R variables. So the problem of partial differential equation is turned into a problem with a single variable. Clearly, a problem with smaller number of variables is simpler than those problems with many variables. So in that sense, there is a great simplification here. Now, this differential equation, ordinary differential equation for capital R, is solved. And then among the solutions, only those solutions which are well behaved are selected. What does it mean? The solution, the function R, should not become infinite at any point in space. What else? It must be continuous as a function of R. Such conditions are used for selecting the well-behaved solutions. I will quote the results from the literature. As a result of this selection process, it is found that the energy values here cannot be just any arbitrary value, but they must be in the following form. Let us write. This equation is the equation for the radial factor R. The name radial comes from this meaning of the variable here, R. It's called the radial variable. Results energy allowed energies are the solution of this equation here results with this conclusion about the energies. That these are in Hartree. Don't forget, our energy unit is Hartree. Let us look at the behavior of the energy using an energy level diagram. The lowest energies corresponds to the lowest value for the integer here because of the minus sign here. So the lowest energy is minus 0.5. This is energy in Hartree. So we can mark it. This is for n equals 1. Therefore, it is the ground state energy, lowest energy. In interpreting such numbers for the energy, please once again remember that there is no absolute energy. All energies are relative. Remember we had said the potential energy has an arbitrariness with an additive constant. So let us remember the definition of reference energy in such problems. This potential energy, charge 1 times charge 2, divided by distance between them. This is the Coulomb potential energy. In terms of R is the variable, distance between the two charges. Which value for R is needed to make numerical value of this expression 0? Which value for R? Infinite. Which means when the two charges are infinitely far away from each other, we say potential energy is 0. This is convention, all right? This is just fixing the conditions under which V will have 0 value. So, this energy here, minus 0.5 Hartree, is relative to that case. In other words, if the electron is infinitely far away from the nucleus, what do we call it chemically? Ionized state. The electron is in the cafeteria and the proton stays here, infinitely far away from each other. That situation is 0 for the total energy of electron plus this proton. Relative to that case, when the electron is nearby the proton, the lowest energy is minus 0.5 Hartree. 1 Hartree in electron volts is 27.2 eV. So if you want to see what this number is in EV, it is just half of this number with minus sign, which means minus 13.6 electron volt is minus 0.5 Hartree. Directly from here, hydrogen atom in its ground lowest energy level. On the right side, what do you see? H plus electron. The plus sign means the distance between the two species, electron and the other, H plus, the proton, is infinitely far away. What is the definition of, well, this describes ionization, isn't it? What is the ionization energy? Total energy of the products minus total energy of the reactant, isn't it? Of course, in the definition of ionization energy, the products must be in their lowest energy level. Here, the products are, one of them electron. What is it's a free electron, of course, infinitely far away. Lowest energy, it has only kinetic energy there. What is the lowest value for kinetic energy? 0. What is the lowest? H plus is just a proton. It also has only kinetic energy. What is the lowest value for the kinetic energy of proton? It's also 0, isn't it? Therefore, ionization energy is simply 0 minus the energy, lowest energy for the reactant. What is the lowest energy? Which is just 13.6 EV. That is the ionization energy. Let us look at some, our time is more than up.